Stiamo registrando, tutto a posto. Okay, I think we can start. Ok, vedete la slide da casa? Vedete la slide da casa?
Sì, si vede.
Okay. So today we start a new chapter of the course, which is about the structure of the proton. How is the proton, or in general the nucleon, made of inside? And this will take 2.5 lessons. So, okay, you can see. So, electron-proton scattering provides a powerful tool, okay, to study the internal structure of the proton. And the reason for using electrons is at least twofold. First of all, because the electrons do not feel the color charge, so they can probe precisely the distribution of the electric charge inside the proton or the neutron. And the other advantage is that ultra-relativistic electron beams are relatively easy and cheap to obtain in any accelerator facility. Okay. Of course, not only electrons have been used to probe the nucleon structure, but also different other probes, such as neutrino beams, but also muon beams, etc. And of course, when one uses neutrino proton scattering, one has to think that this scattering is regulated by the weak interaction, clearly, not by the electromagnetic. Now, at low energies, the dominant process is elastic scattering, of course. Electron-proton into electron-proton, where the proton remains intact. Okay. The incident electron interacts electromagnetically with the proton as a whole, and as we know in the quantum field theory approach, by exchanging a virtual photon. And the process can, however, only reveal global properties of the proton, such as its charge radius, as we will start today. Okay. Of course, if we increase the energy, we are increasing the spatial resolution of our probe, and so we can study the proton into much, much more detail, the proton structure. So at high energies, the dominant process is now deep inelastic scattering, or DIS, where the proton break up in the process, revealing its internal structure. In this kind of process, capital X that you see here in the reaction represents the undetected hadronic final state. The point is that the proton break up. Let me close the box. So the proton break up, and all the quark content of the proton have to hadronize, as we studied last week. Okay, so at the end we observe a bunch of hadrons in the final state that we just generically call X, where X means that in general we don't detect these hadrons, but only the scattered lepton. Now, in this case, as we will study tomorrow, the underlying process is the elastic scattering, so electromagnetic elastic scattering of the incident electron with the elementary constituent of the proton, which are the quarks. And of course, the DIS provides information about many more information about the proton structure, because we have a much more higher spatial resolution, and so reveals, for instance, how the momentum distribution of the quarks is distributed, etc. This we will study tomorrow. So, in general, the spatial resolution of the incident electron depends on the momentum, clearly, through the de Broglie wavelength, and ultimately on the wavelength of the exchanged virtual photon. Okay, and so one can distinguish between 4 different regimes by comparing the wave function of the extended photon with the radius of the proton, for instance, which is our reference scale. So, if the wavelength of the photon is much, much larger than the radius of the proton, then of course electrons are non-relativistic. It's a very, very low energy process. And the process can be described in terms of elastic scattering of the electron, of a non-relativistic electron, in the static potential of an effectively point-like proton. So the resolution of the electron is so low that you cannot resolve the structure of the proton, but you can only see the proton as a point-like object. Then one can increase the energy of the electron beam, and so one can essentially decrease the wavelength of the extended photon. And when this compares with the rest of the proton, one of course can start to see, to gain some more information in the process. In this case, the energy of the electron is high enough to reveal the finite size of the proton. So the proton is not anymore a point-like object, but it has some finite size. And the cross-section calculation in this case need to account for the extended charge and magnetic momentum distribution, as we will study better today. So the distribution are not a delta functions. The proton is not anymore a point-like object, it has some extension. Then we can increase even further our beam energy, and so reduce even further our photon wavelength. When this goes below the dimension, the size of the proton, of course, we can start to reveal details inside the proton. In this regime, the elastic cross-section becomes small, and the dominant process is inelastic scattering, clearly, where now the virtual photon probes the proton internal structure, although still with low resolution, and the proton remains excited. So we excited the so-called nuclear resonances, as we will see tomorrow, I think, yes. And then we can increase even further our beam energy, so reduce even further our photon wavelength, and we are now in the regime of DIS, where the photon wavelength is much, much smaller than the proton radius. In this case, as you can see from the picture, the spatial resolution is so high that the virtual photon can probe essentially the dynamical structure of the proton. Okay, quarks, gluons, etc. Okay, this will be again clear tomorrow. Okay. Now, today we will concentrate on low energy processes, so on elastic scattering processes only. Tomorrow we will move on to inelastic and the deep inelastic. So let's start from the very basic things. So electron-proton elastic scattering. This is dominant at low energies, and therefore a non-relativistic treatment is more than adequate. In this regime, the proton can be considered as a point-like, spinless, charged particle with infinite mass. And this infinite mass approximation means that we can neglect its recoil energy. So the energy involved in the process is so low that we can assume that the proton stays at rest. No recoil. And so the proton is seen in this regime by the electron as a source of a static central potential, whose strength depends only on the distance r. Now, we can make use of our beloved Yukawa potential, that you know now very well, okay? And if you remember, by using the Yukawa potential in plane wave approximation and first order perturbation theory, we derived the transition probability amplitude, TFI, which is a function essentially of the transferred momentum, and we obtain this kind of expression, which, as you remember, in the classical picture, describes the probability amplitude for scattering of a point-like particle, so our electron, which is coupled through a coupling constant G0 to a static potential of intensity G generated by a point-like source of infinite mass. Okay, this is the very basic lowest energy thing that one can think. And if you remember, now in the Yukawa potential, this capital R is essentially the inverse of the mass of our extended boson, in the Yukawa picture. And so when we now substitute G divided by 4 pi as the charge Q, and we set the mass of the extended photon boson, so the photon, to be 0, so the range of the interaction becomes infinity, then we recover the standard Coulomb potential. Okay. In the Yukawa approach, as we just mentioned, TFI is proportional to the boson propagator, so to the probability amplitude for the exchange of a boson of a mass m and momentum q between the two interacting fermions. Okay. Now, in particular, for the case of electromagnetic electron-proton scattering, the exchanged boson is the photon, so indeed m is equal to 0. So we can drop m out of the propagator or the probability amplitude, if you like. The constant G0 corresponds to the charge of the incident electron, so it's just the electron charge E. And the constant G divided by 4 pi corresponds to the charge of the proton. So we can now invert this to get G as 4 pi ZE, but for the case of the proton, Z is equal to 1, of course. Okay, so it's 4 pi E. Okay, now we have all the ingredients, and we can try to derive the shape of this cross-section. Okay, so let me move now to the whiteboard. So our probability amplitude is V0 divided by T squared plus M squared. This is clearly the non-relativistic one, because we don't need now the relativistic approach for this low energy process, where V0 is the electron charge. G, as we've seen for the proton, is 4 pi E. Of course, we want to assume that it's 1. And finally, and we neglect the recoil of the proton. This means that the initial momentum of the electron, pi, is approximately the same of the final momentum of the scattered electron. And so this we can just call P. Now we can calculate transferred momentum squared, so the Q squared, which is pi minus pf squared. So let's elaborate this more. So it's pi squared plus pf squared plus the double product twice pi scalar pf. Now, by making use of this, okay, so this simplified approach, it becomes just twice p squared plus minus minus twice p squared cosine theta. Here we just develop the scalar product, okay? And so this we can write at the end as 2 p squared 1 minus cosine theta, and by the simple trigonometry, it is 4 p squared and then this becomes the sine square of theta. Okay. So now we can, and of course, is equal to 0. So now we can substitute all these ingredients into our probability amplitude. So T F pi is given here, then reduced to, okay, let's write it again, G 0 Q squared plus M squared. We don't have the master, and we will substitute all the rest. So it's going to be equal to 4 pi p squared, and I will have 4 p squared sine squared of theta half. Okay. Now, this is, as you know, the core of the cross-section. Okay. Now we make use of the Fermi-Golden rule to construct the cross-section. So the differential cross-section for the elastic process, okay, at this low energy regime essentially coincides with the total cross-section. Everything is elastic at this energy. So this is essentially equal to the del sigma in the omega total. Okay, and so we can use the formula that we derived starting from the Fermi-Golden rule. So this is 1 over 2 pi squared h bar to the 4. Then we have our position amplitude squared. And then we have, if you remember, Vf Pf squared divided by Pi Vf, where Gf is the spin multiplicity, okay? And then we have the final momentum and the initial final velocities. So we can substitute now our probability amplitude. So this is going to be 2 pi squared h bar to the 4. Then we have our 4 pi e squared divided by 4 e squared sine square of theta half. And then we have vf squared divided by vi df. Now let's make some simple consideration. So starting from still this condition here of the not recoiling proton is equivalent to write Vi is equal to Vf. Which is just let's call this B. And so our term here, Pf squared divided by Vi over Vf, this is nothing else than P squared divided by V squared. Is a full classical consideration, okay? And classically, this is just m squared, right? What about now the spin multiplicity? So in this very simple approximation, we are neglecting spins of all particles, okay? So Gf is equal in general to 2SE plus 1 to Sp plus 1 for the spin of the electron, the spin of the proton. We are now working in the spinless approximation. So this is 0, this is 0, this is just 1. Of course, we will introduce the spin in a second step. And then lastly, we work in natural units. So we have h minus 1. And so we can write down our perception. So let me comment here. So let me write again. Sigma is the form elastic. So what do we have here? We have our probability amplitude 4 pi e squared divided by 4 e squared sine square of 2 factor. Then we have this term here that's reduced to m squared divided by -2 pi squared. So this is 1, this is m squared, and then we have still, this is now 1 in natural units, and we still have to take about this 2 pi. Now we can make a simple thing here. So we divide by 2, so this is 2 pi e squared, and then we have 2 e squared sine square of theta half, and this goes and sorry, this is all square, of course. Right, so we can now remove this, and so we have, we can write this as e squared divided by 2 p squared divided by m sine square theta half. Okay, the last consideration, still in an relativistic approach. Again, from here it follows that Pf is equal to Pi, and so this is p squared over 2m. And so, let me go here. So 2p P squared divided by M is just 4 times the energy of the scattered electron. Okay, so let's just substitute here. Again, we obtain e to the fourth or EF squared and sine the fourth of e to the half. Do you recognize this cross-section? Volume. Do you recognize what it is this? You should have studied for sure in the past. This is the Rutherford cross-section, okay? And it is proportional to e to the fourth and q. So it's a pure electromagnetic or Coulombian process, elastic process, and so indeed we derive the Rutherford cross-section. The fact that it is proportional to the fourth power of the quantum momentum tells you that when you move now to high energy, this cross-section drops quite fast, very, very fast actually. Okay, and this is indeed the reason why at high energy the elastic component of the cross-section essentially disappears, and we only have inelastic contributions. The question?
Yes, Professor, just a question. I've got problems reading, the connection sometimes going blurred. Can you explain again the line regarding the spin, where you explain the GF?
Yes, so in this very, so this guy here.
Yes.
Okay, so in this very, very first approximation, we are considering only spinless particles. So the spin of the electron is 0, and the spin of this is an S, 2sp and 2sp. So we are assuming that the spin of the electron is 0, and the spin of the proton is also 0. This very simple approximation, okay?
Okay.
And so the spin multiplicity goes to 1, trivially, okay? Now we will remove step by step all our approximations, and so we will also introduce spin at a certain point, okay?
And what you wrote on the right, n is on the right of that line.
This guy?
Yeah.
This is the natural unit, so h bar is equal to 1.
Okay, thank you.
You're welcome. Okay. Okay, so indeed we obtained the Rutherford cross-section for 2 point-like spinless particles of charge A. As I was saying, the angular dependence of the Rutherford cross-section, so this sine squared to the fourth here, only originates from the 1 of q squared term in the propagator, if you remember, from our derivation. And as I was mentioning, the dependence with the inverse of the fourth power of q implies that very low event rates for electron scattering with large momentum transfer are expected. Okay, and in fact, the large q square elastic scattering is suppressed. Now, the Rutherford cross-section has been derived from first-order perturbation theory, and by considering a non-relativistic spinless electron in the static Coulomb potential of a spinless and infinitely massive proton. So we have made use of a lot of approximations in this derivation. So let's now start to remove one by one all these approximations. So the next level is represented by the so-called Mott scattering. Okay. In this limit, now the electron is relativistic, so we are increasing the energy of the beam, and so it is. And so we have to take into account its spin. So in other words, we are now considering the electron as a Dirac particle. Okay, a solution of the Dirac equation. However, the proton is still considered spinless, and we can still neglect its recoil energy. So we are still in the approximation of infinite mass of the proton. And this condition applies where the energy of the electron is intermediate between the mass of the electron, so it is of course relativistic, but much smaller than the mass of the proton. Okay. Now, if you remember now from QED, for relativistic electrons, there are only two possible helicity configurations that lead to non-zero current, right? So U plus and U minus are the helicity spinors, if you remember. Okay, so this is these are the only two combinations that provide conservation of helicity in electromagnetic processes. Now, one can now use the full expression of the helicity spinors that I gave you in the Dirac chapter, okay? And inserting the expression of initial and final state electron helicity spinors and treating the proton still as a point-like infinitely massive object, one obtains this expression for the cross-section, which is now the Mott cross-section. So it is essentially the Rutherford cross-section multiplied by this correction term, 1 minus beta squared sin squared θ. Okay. Now, since we are treating electrons as a relativistic object, we can, of course, work in the limit where beta goes to 1. And so we have just 1 minus sin squared that gives us a cos square. Okay, so essentially the Mott cross-section is nothing else than the Rutherford cross-section multiplied by a cos square of θ, where θ is the scattering angle. Okay, let's now see what is the implication of this cos square term here. So this additional cos square term has the effect of suppressing backscattering processes. So where the electrons scattered at 180 degrees backward. Okay, why do we want to have this suppression? This is all about angular momentum conservation. So suppose we have an incoming electron with a momentum p, okay, and a spin aligned with the momentum. So in a positive helicity configuration, okay. And in our approximation, the proton is spinless, okay? So being spinless, it cannot absorb any change of the spin of the electron, okay? It is just spinless, a scalar object. Now, when the scattering is backward, okay, so 180 degrees, of course, the momentum now points in the opposite direction, but the spin is still there. It's still pointing in the same direction because there is no way for a spinless proton to absorb the spin flip. Clear? So we started from a configuration where the incoming electron had a positive helicity, and we are now in a configuration where it has a negative helicity, where the spin points in the opposite direction to the momentum. And since helicity is conserved in electromagnetic processes, this cannot happen. And indeed, this is killed by this cos θ square. When θ is 180, this term kills the cross-section. Okay. So the process cannot occur for relativistic electron as a consequence of helicity conservation in electromagnetic process, and this is indeed guaranteed by the cos square θ term. Now, let's again move on. So let's increase it even more now the energy, okay? And if we now increase sufficiently the energy of the scattering in the scattering process, we can no longer ignore the proton recoil energy. So we are now in a situation where we cannot anymore assume that the proton is infinitely massive, okay? And as a consequence, the final energy of the electron will be different than the initial state because part of the energy is absorbed by a recoiling proton. And by simple kinematics, okay, one can obtain that the energy of the final of the scattered electron is related to the energy of the incoming electron by this relation here, okay, which depends also on the scattering angle. So now we can correct our Mott cross-section, including this finite mass regime, okay, where the proton is not anymore infinitely massive. And we just have to multiply the Mott cross-section by this correction factor, okay, which is given by this formula here. Okay. Of course, when using this formula, when you put the mass of the proton to infinity, these terms goes to 0, and all these object goes to 1. So we get back to the previous Mott cross-section. Now, one has to be careful now because at this higher energy, a relativistic approach is now mandatory. Okay. And it is not possible anymore to describe the scattering in terms of the 3 momentum transfer, but we have to move to the Lorentz invariant square for momentum transfer. Okay, so let me now move to the whiteboard. So we talk now about 4 momenta, not anymore 3 momenta. Okay, so this is now initial for momentum minus final for momentum squared. And so this you know very well is EI minus EF squared minus EI, now it is the 3 momentum, plus, no, it's a minus, PF squared. And so we have EI squared plus EF squared minus twice EI EF minus EI squared minus PF squared plus twice PI dot EF. Now, let's now merge this. And now we are left with the mixed terms. Now here we recognize this is the mass of the incoming electron squared. This is the mass of the outgoing electron. This is the mass of the electron squared, right? And so this we can write as twice mass of the electron. And now here we have minus twice EI EF minus EI EF cosine theta. Okay, but we are in a relativistic regime, so for sure we can neglect the mass of the electrons, and we can neglecting the mass of the electrons, even we can equate the energy with the momentum. Okay, so this is at the end simplified as minus twice EI EF 1 minus cosine theta. That corresponds to minus 4 times EI EF times square of theta. Which by construction is negative. And we will comment on this in a moment in the slide. Okay. And on the purpose of working with the positively defined quantities, one defines the capital Q square as minus Q square. So this is 4 pi EF sine square the half, and it is of course positively defined. Okay. So this is our Feynman diagram for electromagnetic scattering between the electron and the proton. And it is, as you see, a T-channel process, as we studied in the past, okay? And if you remember, the Q square is always negative for T-channel processes, if on your notes. This means that the square of the time-lag component of Q is smaller always than the sum of the square of the space-lag component, okay? And in this case, the extended virtual photon virtual particle is called the space-like. So we have a space-like extended photon. On the contrary, if you remember, Q square is always positive for S-channel processes, okay? Where now the square of the time-lag component of Q is always larger than the sum of the square of the space-time components. And in that case, the extended virtual particle is called time-lag. Okay, this we studied already. So, this is not the end of the story, of course. So we have still to introduce the spin of the proton. Okay, we know that the proton is a fermion with spin 1/2. So the next level of approximation is now to include the spin of the proton, which can now be regarded as a point-like Dirac fermion. Okay, such as the electron. And so, by doing so, we have two objects that are interacting, and that both carry spin, and so they both carry magnetic moment. And so we have to take into account for the interaction of the magnetic moment of the proton and the electron, once we allow for both particles to have spin. And so we have to modify again our cross-section. Okay, let me call this the Dirac, because now we are treating both electron and proton as Dirac particles. So indeed, this corresponds to the addition of a new term, which goes like the sine square of θ². Okay. So overall, we can write this as a Dirac as still elastic cross-section, but fully relativistic, as the Rutherford, corrected by the finite mass of the proton, corrected by the Mott term. Okay. And now with this initial term, which accounts for the interaction of the magnetic moment of electron and proton. Okay. Now we can put the cos square outside, so we can recover, and we can also merge this together with the kinematic factor, so we can recover outside our Mott cross-section for the finite mass proton, and we are left with this correction term. Okay. This is again not yet the end of the story, because we know that although the electron is a pure Dirac object, so it comes with the magnetic moment equal to the Bohr magneton, plus correction coming from the loop, QED loops, as we studied. This is not the case for the proton and the neutron. Okay, proton and neutron, we know that are composite objects, and we have already studied that the magnetic moment of the proton is very different than the Bohr magneton. Okay, there is a correction factor 2.79 for the proton and minus 1.91 for the neutron. And this we can separate in this way. So this object we can write as 1 plus the anomalous part of the proton magnetic moment, which is 1.79. And also for the neutron, we can split this into 1 plus the anomalous component, where 1 means exactly the Bohr magneton, what we would expect for a Dirac particle, and it is the anomalous contribution, the anomalous part. Okay. Now, once you take this into account, we have to correct once more your cross-section. So let me call this Dirac with anomalous magnetic moment. So it is the Mott with finite mass of the proton. And now we have to introduce these anomalous contribution, magnetic moment terms here in the cross-section. So the cross-section is becoming each step more and more complicated and less approximated, of course. Clearly, the approximation makes sense. It depends on the energy scale of your process. If you are very low energy, then the Rutherford cross-section is perfect to describe your data. If you increase energy, it is not anymore sufficient. Now, yes. Okay, we have still one level of approximation. That is, we are still considering the proton as a point-like object. Okay, so it has some spin, it has some anomalous magnetic moment, but up to now, it is still a point-like object. Now we want to remove this additional approximation, because we know that the proton is an extended object, as well as the neutron. And so we want to take out essentially the non-point-like distribution of its electric charge and its magnetic moment. Okay, and this is done in terms of the form factors that we will now derive. So what we follow is a pure classical derivation. Okay. So, suppose we have a spherical distribution of electric charge, which is our proton, if you like. Okay. And we want to calculate the Coulomb potential at a certain point P, which is at a distance r from this geometrical center of this spherical distribution. Okay? Let me take a generic point here, P prime, inside the distribution, whose position is given by the vector r prime. And so this vector is now r minus r prime. Now, you know from classical physics that the Coulomb potential given by a charge distribution at a certain distance r is given by the integral of the charge distribution divided by the distance. Integrated over the volume of our charge distribution. Okay, so this is the Coulomb potential at a certain distance r from a spherically distributed, not necessarily spherically, but from a certain distribution of electric charge. Now, we can factorize this object, so the electric charge distribution, as the total charge and the spatial distribution of this total charge, which is recorded as given by simple function at r. Okay, this is equivalent. And of course, when you integrate this over the volume of our distribution, you have to take the total charge Q. So we need to normalize things such that the integral of the charge distribution, the volume must be new by construction, by definition. And so we need to run down a problem where this normalization condition which translates the condition on our spatial distribution. Okay. So we need to impose that f prime in the volume must be equal to 1, such that the integral in the volume of the charge distribution is equal to the total charge. And this we can now develop in spherical coordinates. So this is the integral from 0 to pi, integral from -1 to 1, integral from 0 to infinity of f r prime in the phi, the cos theta, r prime squared. Yeah, so this is the volume integral in spherical coordinates. Now, our integral does not depend on the azimuthal nor on the polar angle, so we can trivially solve this part here, which is 4 pi. So this is 4 pi, and then we are left with the integral over space, spatial coordinates, from 0 to 3. And this must be equal to okay. We will make use of these later. Okay. Let me now clear the board. First, we should be. Let's compute now the transition probability amplitude. As usual, we put here our potential and initial time state. So this in plane wave approximation in first order of perturbation theory and in a non-relativistic approach is simply given by e to the minus I here, then we have our potential, and we have e to the I, ei scalar r, in the volume. Now, as usual, we define the transfer momentum as P high minus Pf. So we can merge now these two exponentials, and we can now substitute the expression of the Coulomb potential that I gave you before. Okay. So this is going to be double integral E I Q scalar R minus R. Then we have our potential, which is rho or R prime divided by 4 pi R minus R prime. And now we are integrating with the cube of prime, which is coming from this part here, from the Coulomb potential, and then we still have dq r. Now we make a trick. So we multiply and we divide by the same quantity. So here we can write as double integral e to pi q scalar r minus r prime times e to pi q. So we are multiplying and dividing by this here. Now we can write our charge distribution as q times f r prime 1 over pi r minus prime, and then we have to integrate these all the ones. Now let me define this quantity as R. So capital R is the difference between R minus R prime. So we can rewrite this integral as integral e to I q capital R. Then we have q divided by 4 pi R. Then we have our f R prime e I q R prime the cube capital R the cube R prime. Okay. Now we are dealing with low energy elastic scattering. Okay. So in low energy elastic scattering, the transfer momentum Q is relatively small. Okay, and this corresponds to the distance being relatively large. So it corresponds to the case where R is much larger than R prime. Okay, your resolution is very small, so you are far away from your distribution here. You can consider as small as you want. And in this approximation, you can now split this integral into two terms, into the product of two terms. You can factorize this. Here. So the first term is e to the pi q r cubed by the 4 pi r in the cube r times integral of f r prime. What is that here? E to the I cubed scalar r prime in the cube r prime. So in this limit here, we can factorize this integral into these two contributions. So in this part, in this first integral, we don't have any information about the distribution of the charge. We just know the total charge. Okay. So this is the scattering amplitude for the scattering of a point-like object of charge Q. The other term is our correction now, because our object is not anymore point-like, but it has some charge distribution. Okay, so this is the scattering of a point-like object, and we have to correct this in order to take into account the finite size of the proton. Okay, so this is the standard amplitude for point-like, and this is what we call the form factor. Or elastic form factor of the proton. And so overall, we can write down our amplitude as the probability amplitude for a point-like proton times a form factor, which tells us how actually the charge of the proton is distributed in space. Okay. So this you find also in the slide. Okay. So now look at this object here. Okay. So what is the goal of our game? Is to learn how the electric charge is distributed inside the proton. Okay. So what we need to know is indeed the f function, the small f function. Okay. And in principle, one can measure the form factor in the way that we will show you later. Okay. So in principle, by inverting this expression, so by doing the inverse Fourier transform, after measuring the form factor, one can derive the shape of the charge distribution. Okay. So let me read here. The exact form of the form factors depends on the charge distribution. Under some simplified condition, as you see here, this is nothing else than the Fourier transform of the charge distribution. And so one can, in principle, invert these and extract the charge distribution as the inverse Fourier transform of form factors in the hypothesis that you can measure these experimentally. Okay, so you can measure the Q dependence of your form factor. However, so mathematically this works perfectly. Physically, it's not so easy because in practice it is not very accurate because the form factor FQ can only be measured in a limited range of Q. Okay, you cannot measure from Q from 0 to infinity. And the reason is that the elastic cross-section goes down very sharply at large Q square, as shown before. Okay, so we cannot cover the full range of Q, and so we cannot really use this approach to extract the charge distribution. So the common approach is different. Okay, is to find a reasonable parameterization of the form factor and then to fit our data with this parameterization. Okay, and so to fix the free parameters by fitting data. Now, in all practical cases, the charge density is assumed to have a spherical symmetry. There is no reason not assuming this for proton. Okay, and as a consequence, we don't need any more now the direction here, but we just what only matters is the distance r. Okay, not the direction, so not the vector anymore. And so this translates to the fact that the dependence of the form factor in practice is just on the modulus of Q, or Q squared. Now, the form factor can indeed be calculated analytically for some charge distribution which are described by simple radial functions. And you see here some examples. Suppose that your proton is really point-like, so your charge distribution is a delta. Okay, then when you take the Fourier transform, the Fourier transform of these, you obtain a flat form factor. Sorry. Okay. Suppose now that the charge distribution is exponential, then when you calculate the Fourier transform of this function, you get a so-called dipole function, which has this kind of trend. If it is Gaussian, and you calculate the Fourier transform, you get again a Gaussian, but with a different width. If it is a homogeneous sphere, okay, like this, a very sharp sphere, then you obtain some oscillating behavior, etc. Okay, so there is through the Fourier transform, there is indeed a connection between the shape of the analytical shape of your distribution, so your model, okay, and what you can actually measure from your compactors, and vice versa. Now, if now the transfer momentum Q is small enough, because we are still in the regime of elastic scattering, okay, one can perform a power expansion of this quantity and derive the so-called proton mean square charge radius. Let's do this, and then we'll make a break. Well, let's start from the definition of our form factors. Okay, FQ squared. So as you've seen, this is the Fourier transform of the space distribution, and we have E pi Q scalar R prime in the R prime Q. Sorry, let's take it. Now, this is with the middle step of here, the scalar product. So this is the step R prime, E to I, Q, R cos theta, R prime cos theta, and then we have B. Now, since we are at log 2 square, log 2, we can perform a power expansion of this exponential. So this is going to be integral of f r prime, and the power expansion is the sum of n goes from 0 to infinity of 1 over n factorial, and then we have the exponent, so I q r prime cos theta to the n power. Okay, so let's now develop this power expansion, and let me also make explicit the volume integration into spherical coordinates like before. So we have integral 0 to infinity, integral from -1 to +1, integral from 0 to pi. This is our integral of the volume. Then we have f r prime. Now we can develop this guy here. So when n is equal to 0, it is 1, it is 0, so everything is 1 here. Now when n is equal to 1, we have 1 here, 1 there, and so we have this quantity here, r pi, q r prime cos theta. When n is equal to 2, then we have 1 over 2. And then we have to square this. So the minus sign comes from the square root of I. And then we have q r prime squared cos square theta. And then we can go up to infinity. Infinite term. And now we have our integration variable. So it's I, the cos theta, r prime squared d theta. Okay. Now let's split these integrals because we have now infinite terms here. So let's make infinite integrals. The first integral is just f times 1. So there is no angular dependence, so we can already put 4 pi outside. So this is 4 pi. And then we have the partial integral of f r prime from 0 to infinity, r prime squared with r prime. And this is the first piece. Now we go to the second piece, plus 2 pi, we can integrate over phi, but not over theta, because we have now theta in the integrand, okay? So plus 2 pi q I, and then we have the integral from 0 to infinity, the integral from -1 to 1 of cosine theta in the cosine theta. Let me, okay. And then we have still f r prime cube in the r prime. One comes here and the other two. And this is the second piece. Now we go to the third piece. Minus 1/2 q squared 2 pi integral from 0 to infinity integral from -1 to 1 of cos squared theta in the cos theta f r prime to the fourth d r prime plus infinite other terms, infinite other integrals. Now, this integral is trivially 0. So the first order term disappears. Okay? This integral, you can check yourself easily, is just 2/3. So we can now simplify our question. So we have first term here is the same. Then the second term drops, and then we have the third term here, which is now we can fill 1/6. Then we have 4 pi q squared. And then we have the integral from 0 to infinity of f prime r prime to the fourth power d r prime plus infinite terms. Can you recognize this? What is it about? Go back on your notes. You will find the answer in your notes. Come on. This is the normalization condition, right, that we showed before, in order to have a total charge Q for our distribution of charge. So this is just one. And so this we can write as 1 minus 1/6 q squared, and then all the rest we will get in a compact way as r squared average. Plus, again, infinite terms, where this object here, which is indeed our looking square radius, is 4 pi integral of r prime squared, where hidden is f r prime squared d r prime. So this is the proton mean square radius. Okay. So now we can invert this object to obtain the proton mean square radius. Proton. So from f of q squared equal to 1 minus 1/6 q squared is radius plus blah blah. One can invert. Actually, one can derive this. Sorry, with respect to q squared. We take the derivative that q squared divided by the q squared, and this is going to be minus 1/6, and this disappears. Now we simply have our r squared plus terms, infinite terms which depend on the q squared. Okay. Now we can invert this to obtain our proton root squared as minus 6. And we have the derivative squared. And in order to get rid of all these infinite higher order terms, we just ask this to be calculated as q squared equal to 0. Okay. So this is the way to calculate the proton mean square. We can also express this in an equivalent way. Let me do this in a moment. Okay, switch. So what you obtained was 4 pi, then the integral of r squared f r prime squared in prime. So let's make essentially the inverse process. So let's go back in our derivation. So this is the integral from 0 to 2 pi of pi, integral from -1 to 1 of d of theta, integral from 0 to infinity of r prime squared, that's r prime squared r prime. It is integral from 0 to 2 pi, integral from -1 to 1, integral from 0 to infinity of r prime squared f prime, and then d phi equals theta r prime squared d phi prime. This we can now write back in the compact way as f of r prime squared z cube r prime. Okay. And now we can multiply and divide by the total charge, total electric charge. So this is f prime r prime squared z cube r prime times capital Q divided by capital Q. And as we've seen before, when we introduce the normalization of the spatial distribution of the capital Q, we can write as, so the numerator now is our charge density, so it's rho of r prime squared z cube r. And in the denominator, we have just the integral of the charge distribution in the volume. Okay. So indeed, we have two equivalent ways to express our proton root square radius. It is what it is. Okay, let's make a 5 minutes break. Let's recombine at 25. Okay. So we recombine at 25, 10:25. Okay. Okay. So let's go now on the slide. So let's summarize our results for the proton root mean square radius. Okay, so we derived in this form here, but the experimental way to measure it is by derivating the form factor analytical shape in the limit where q squared goes to 0. Okay, and we can also compute it using this expression. So let's now do an exercise on this. So let's calculate the root mean square radius of a particle with a mass 0.84 GeV and with this charge distribution. So rho 0, and then we have an exponential. So we have a mass of 0.84 GeV, and we have a charge distribution to R here by constant, and then an exponential distribution, and T divided by H bar R. So we want to calculate our root mean square radius. And so we use this. So 0 R and R is R squared, and then QR divided by rho R in the QR. And we just substitute our charge distribution here. So this is 0 e to the minus mc over h bar r squared the QR. Yes. And then we have the integral of rho 0 e to the minus m c divided by h bar, and then in the bottom. So let's now put this integral in the stereo coordinates as usual. So we're going to have an integral from 0 to pi in the pi, integral from okay, right, so from 0 to pi of sine theta, theta, integral from 0 to infinity of rho 0 e to the minus m c divided by h bar. And then we have r to the fourth. Yeah, cioè cosa? Certamente, grazie. And now, the denominator 0 to pi, 3, 0 pi, sin theta, theta, 0 infinity, rho 0 e to the minus mc over h bar r squared. Yeah. So we have the fourth power here and the second power here. Now we don't have any angular dependence in our charge distribution, so all this drops down and also the constant drops down. So we are left with the integral from 0 to infinity e to the minus mc over h bar r to the 4 in the r divided by integral from infinity e to the minus mc h bar r to the second power in the r. Now, these two integrals are of the form integral of p to the minus half r to the n in the r. Okay, they are both of this form here. And it is a known integral that can be solved by parts. And the solution of this kind of integral is n factorial divided by alpha to the n plus 1. And so we can already write down here the solution of these two integrals. In this case, n is equal to 4 in the numerator. So this is 4 factorial. And then we have the argument that is mc divided by h bar 4 plus 1. And then the numerator n is equal to 2. So we have mc divided by h bar with the 2 plus 1. Now, let me continue here. So now we can simplify things. So this is just 12 divided by mc over h bar squared. Okay. And we can also multiply by c here. So this is divided as 12. And then we have c squared divided by h bar c squared. Now we substitute all our data. So this is 12. The mass of the particle is 0.84 GeV, so the value is 840 MeV. This is a known constant, you know, it's 230. So this is going to be 12 times 200 squared divided by 840 squared, 30 squared. It is 0.68 Fermi. And so we can take the square root of this mass, which is the square root of the Root square radius. So this is the square root of 0.68 Fermi squared, and this is the 0.82. Okay. So this is the average radius of this particle. Well, radius means radius of the charge distribution of this particle. Okay. Okay, so let's continue now our story about the cross-section. We interrupted at a certain point because we had to introduce the form factors. Let me recap our previous result. Okay, so this was the cross-section of elastic scattering, where the proton is now a Dirac object. Okay, where we also take into account the anomalous magnetic moment. So this was the relation that we obtained. Now, at this point, the proton is still point-like. Now we introduce the space distribution of the charge, okay, of the proton, and so we introduce essentially the form factors. So we can now write down our cross-section, which is now much more refined, as you see. Now we're introducing these two objects, which are F1 and F2, which are known as the Dirac and Pauli form factors, respectively. Okay. So essentially, the shape of the cross-section is the same, but where you have one that corresponds to a point-like object, now we have to take into account for the distribution of the charge, okay, of this object. So the cross-section becomes now more and more complex, okay. Now, electron-proton elastic scattering cross-section is, however, more conveniently expressed in terms of a suitable combination of these Pauli and Dirac form factors, okay. which are known as the electric and the magnetic form factors. So the electric form factors, GE of Q, is defined as this combination of F1 and F2, okay? And GM is given by this different combination of F1 and F2, okay? So the GE describes the distribution of the electric charge, and GM is the distribution of the magnetic moment in the proton or in the neutron, okay? Now, in the limit where Q squared goes to 0, okay, so we don't have any more any spatial resolution, so again, we look at the proton as a pointer-like object. These quantities are normalized to the electric charge in unit of E, so the electric form factor of the proton is 1, the electric form factor of the neutron is 0, okay, that's the electric charge. And for the magnetic moment, this corresponds to the anomalous magnetic moment of the proton and of the neutron, okay, when you are very far away, so very low spatial resolution. So now we can rewrite our cross-section in terms of this electric and magnetic form factor, and this is called the Rosenblood formula, okay, which takes this shape here, okay. Now, a few comments on this formula. So when you work at very low Q square, now we define tau, this quantity here. So low Q square means low tau, okay. Then it is the electric form factor that dominates. One can neglect the magnetic form factor in this regime. Okay, so essentially when you divide the Rosenblood by the MOT, or finite mass, only this guy here survives. This is essentially 0, and this is 0. Okay, we can neglect this. So it is approximately equal to just the electric form factor squared. On the other hand, when we now work at high Q square, so where tau is now much greater than 1, one can neglect the electric form factor, and only the magnetic form factor essentially survives. Okay, so now this ratio is expressed as GM squared plus this term here, okay, which comes from here. One is here, one is there. Okay. Now let me now summarize all we have learned so far. Okay, so we started from the Rutherford cross-section. So the scattering of a point-like spinless electron on a point-like infinite mass nucleus, and we obtain the Rutherford cross-section. Then we increase our energy, so now the electron is relativistic and has spin, okay, so it is a Dirac particle, and we obtain the Mott cross-section, okay, which has this cos-square term that allows to suppress the backscattering in case of the proton, in case the proton is spinless. Then we introduce the finite mass of the proton. So the proton now does a recoil, okay, and we obtain now this cross-section. Then now the proton is now considered as a Dirac particle, so a point-like but carrying spin, and so we have to take into account of the spin-spin interaction or the momentum-magnetic interaction, and so we get the additional sine square theta. And so at the end, we rewrote our cross-section in this way. And finally, we now take into account from the finite distribution of charge and magnetic moment inside the proton, okay? So we express our cross-section in terms of form factors, electric form factors and magnetic form factors, okay? So we removed step by step our initial approximations, which goes in parallel with increasing energy as in a certain sense, okay? Now, how can we measure these guys experimentally? Experimentally, the Q-square dependence of the electric and magnetic form factor can be inferred from elastic electron-proton scattering by varying the energy of the electron beam. Let's see in which way, okay? So the differential elastic cross-section is measured at a specific angles, like look at the picture here, for instance, at 75 degrees, okay? But at different energies of the incoming electron. And different energies of the incoming electron corresponds to different values of Q square through this kinematic formula here, okay? So you fix your angle of your spectrometer, you increase your value of the energy, and you obtain this kind of distributions, okay? Then you change your angle, and you do again. You change your angle, do again, at the end you obtain this kind of set of data. Once you have this, okay, now you fix your Q square to a certain value, okay, and instead you compute your cross-section at a fixed Q square, but at different angles, okay? You have essentially a two-dimensional distribution. So you fix one dimension, you work on the other direction, the other dimension. And so you can now report your cross-section, which is given here as the ratio of the Rosenblood with the Mott, as a function of the angle at a fixed Q square. So let's take, for instance, 292 in this example, okay? So here we have not exactly the angle, but the square tangent of the angle. Okay, and so these are your data. Now, if you look back now to your Rosenwood formula, normalized by the Mott term, so it is just this, you recognize that when you plot these as a function of the tangent square, it is like the equation of a line. Okay, this is the constant term, this is the slope, and this is your independent variable. So you can make use of this in a simple linear fit of your data. Okay, so you can extract both the electric form factor and the magnetic form factor by fitting this distribution with a slope, with a line. And once you do this, you extract the parameters of this line, where the first parameter gives you this term here, which contains both the electric and the magnetic form factor, and the slope of your line gives you the magnetic form factor. So from here, you get GM, you put GM here, you get also GE. Okay, two variables, two unknowns. And so this is the way, it is called the Rosenwood separation technique. This is the way to measure both the magnetic and the electric form factor of the proton in elastic proton scattering. Electron proton scattering. This was done for a specific value Q square, then you repeat for different value Q square, and so now you have your form factor as a function of Q square. And they look like this. So you see here the form factor, the magnetic form factor and the electric form factor as a function of Q square. And the point are, of course, experimental data, okay, obtained in this way through the separation, the Rosenblood separation formula. So what we can learn from these distributions? So the measured form factor, first of all, decrease with energy, okay, or with increasing Q square, if you like, okay. And this is a very important result because this provides an experimental demonstration that the proton has a finite size. Why? Because if you increase your Q square, you are increasing your spatial resolution. And so you are probing a smaller and a smaller volume of your proton. Okay? And so if you get different results, this means that the proton is an extended object, as one expects. The second result is that, as you can see, the form factor essentially goes asymptotically to 0 at very large Q square. And this is also expected because when the form factor goes to 0, the cross section goes to 0, and indeed the elastic cross section goes to 0 at I2 square because then inelastic processes arise. So all this makes sense. One can say even something more. Okay, if you now compare the magnetic form factor with the electric form factor, you see that essentially they scale by the same factor. So they show essentially the same kind of distribution apart from a factor which is given by the magnetic moment. And we can make use of this and of the normalization after the limit where Q square is equal to 0 to relate the two. So the measured values when extrapolated at Q square equals 0 are in agreement with the expectation that the electric charge of the proton is 1 and the magnetic moment of the proton is 2.79. And in fact, this is what you see here. The electric charge of the proton in the Q square equals 0 limit is 1, and the magnetic moment of the proton is 2.79. Okay, so this is consistent with the expectation. And if you take the ratio of the two, it turns out that this is exactly the anomalous magnetic moment of the proton. Okay, so the distribution is exactly the same apart from a constant term, which is the magnetic moment of the proton. For the neutron, instead, the charge is 0, of course. So when we go now to Q square equals 0, we obtain the 0 value for the electric form factor. Now, the experimental data in the low Q square region are reasonably well parameterized by an empirical function, which is known as the dipole function that you see here, okay? Which incorporate this scale law, the fact that the magnetic and electric form factor scale by the anomalous magnetic moment, okay? So you can essentially describe both, apart from this constant, by this dipole function of Q square. Now, back to our discussion that we had today, one can take now the inverse Fourier transform of this distribution, so of our form factor, to get, in principle, our charge distribution or magnetic moment distribution of the proton. Okay. So once you do so once you take this analytical shape of your form factor and you calculate your inverse Fourier transform, you indeed obtain the charge distribution in case of the electric form factor and the magnetic moment distribution in case of the magnetic form factor. Okay, and for the charge distribution, one obtains this kind of exponential relation. So the inverse Fourier of a dipole function is an exponential, and these parameters are fixed by, of course, fitting experimental data. So the proton is not a sharp sphere, okay? It is a kind of diffuse object, okay? So these results make sense, okay? To have a exponentially decaying charge density. Now, let's do this other exercise. So show that the electric form factor, oh, maybe this you can do yourself as an exercise. So show that the electric form factor of a charged particle with a charge distribution given here has indeed the typical dipole form. Let's see. How much time we have? Oh yes, okay, we can make it. So again, we start from our compactor, which is the Fourier transform of the charge distribution. Where the charge distribution given by the text is ρ0 and then e to the minus r. So it's just the one that we saw before, but in natural units. Okay. So let's substitute here. So we have 0, e to the minus r, e to the I q r in the cube. Now this we can put those here outside. The integral is the integral of e to the minus r times e to the I cube r cosine theta in the cube r. Now, as usual, we move to the spherical coordinates. So we have 0, integral from 0 to pi, from 0 to pi, and theta, from 0 to infinity. And then we have our partial distribution. R square integral. Now, we don't have any azimuthal angular dependence, so this is just 2 pi. So we have 2 pi for 0, integral from 0 to infinity, e to the minus 10 r. And here we englobe our polar angular integral, okay, which is essentially minus 1 to 1, e to the I q r cosine theta in the cosine theta. And then we are left with r squared in the r. So we have 2 pi to 0, integral from 0 to infinity, e to the minus n r. This is a trivial integral of an exponential function. Okay, so the result is simply 1 over I q r, e to the I q r minus e to the minus I q r. And then we have r squared here. You can simplify r and r on the exponential here. So this turns out to be 2 pi for 0, integral from 0 to infinity of e to I q r minus e to minus I q r, e to minus n r, r in the r. And now we can split this into two integrals. So we have 2 pi over 0 divided by the pi cube from here. And now we have integral from 0 to infinity t to the minus pi cube plus m r dr minus integral from 0 to infinity e minus pi cube plus m r dr. Let me call this integral A and this integral B. Again, both integrals are of the form the one we've seen before. And if you remember, the solution was n factorial divided by the argument of the exponential to the n plus 1. In our case, actually in both cases, n is equal to 1 because the exponent of r is equal to 1. So the solution in both cases is of the type 1 over alpha squared. And so integral A is given by 1 divided by m minus pi cube squared, and integral B is equal to y 1 minus 1 divided by plus n plus pi cube. So okay, I put the solution of these two integrals. Simple trivial algebra. I will skip this, but you can do the exercise. After a few passages, I obtain 8 pi 0 m to the cube 1 divided by 1 plus q squared divided by m squared squared. Simple algebra. And so this we can at the end rewrite as 1 plus q squared divided by m squared to the minus 2, which is indeed our dipole distribution. Okay. Now, what about the mean square radius of the proton then? Okay, and also of other particles. So the mean square radius of the charge distribution of the proton and of the magnetic moment distribution of the proton and the neutron are approximately the same and can be both calculated by extrapolating the slope of the dipole distribution at q squared equals 0. So essentially, we can make use of the relation that we derived before for the root mean square radius, but using this now dipole analytic form that essentially fits our data. Okay, and it does fit quite well. You see here, the line here is a dipole formula. Okay, so we can use this to calculate our root mean square radius for the charge distribution and for the magnetic distribution of protons and neutrons. And when you do so, okay, in the limit where Q squared is equal to 0, so you can neglect all the higher order in the power expansion, you obtain 0.66 squared Fermi, and so you take the square root and you get 0.81 Fermi. So this is, let's say, a hint of the size of the proton, of the radius of the proton. However, this is not completely accurate, because one can show that the dipole distribution works pretty well, but not perfectly well. Okay, so instead of using here the dipole distribution, one can actually extrapolate the real data, so not the analytic function, but the real data essentially, to the limit where Q squared goes to 0. And by doing so, one obtains now the most accurate value of the charge radius of the proton. Okay, which is 0.88 Fermi. Okay, a bit larger. Now, what about neutrons? So neutrons are a bit more complicated to handle because they are neutral. So essentially, you cannot have a target of neutrons, for instance. Okay? It's a bit more complicated to measure form factors. So the neutrons appear electrically neutral, but only outside. Of course, in the interior, they contain electrically charged constituent, which also possess spin and so magnetic moment. Okay? So the experimental study of the neutron form factor is a bit more complicated because one cannot make use of pure neutron targets. There is no way to build pure neutron targets. What one can do is to use a deuterium target, which is a bound state of proton and neutron, as you know. Okay, and then you have to correct your result by the binding energy of the proton and the neutron inside the deuterium. So you assume that the scattering occurs on the neutron, but then you have to correct for the binding energy because the neutron is not free, but it is bound inside the deuterium. Okay, so there is a smaller nuclear effect that had to be taken into account. Once you do so, one can nonetheless obtain the shape, the Q square dependence of the form factor. In particular, you see here the electric factor of the neutron. And in fact, when you go down to Q square equals 0, you have to obtain 0 because the neutron from outside is a neutral object. Okay. When you look more into the detail inside, you see that there is indeed a distribution here, which arises from 0 up to something like 0.5, 0.6 at a Q square of 0.3 GeV, and then slowly decrease. Okay, so we have also measurement of form factors for the neutrons, not only for the protons. What about other particles like the pion or the kaon? So what about the mesons? Can we see how the charge distribution or the charge is distributed inside the meson? Can we also calculate the root mean square of a meson? Yes, we can do this, but of course the technique must be different. Again, we cannot have a target of pion or a target of kaon. Okay, so we have to use the inverse process. We can make a beam of pion and a beam of kaon, and we can make a scattering between the beam of pion and kaon on the atomic electrons of your target. So it is an inverse reaction. Okay. And then at the end, the form factors are determined by the analysis of the angular distribution of the scattered electron. Okay, so now the electron is at rest and your pion is coming as a beam of particle. Now, if you remember, pions and kaons are pseudo-scalar mesons, so they have no spin and so they have no magnetic moment. So the only thing one can measure is the electric form factor. And for the case of mesons, the Q square distribution is a bit different. It's given by a monopole distribution, not anymore a dipole, but a monopole distribution that you find here. So you see here now experimental results for the electric form factor of the pion as a function of Q square and of kaon as a function of Q square, okay, fitted with this monopole distribution. And then, using the way we described today, one can extract the root mean square, and you see here the value for the pion and for the kaon. Okay, the kaon is a bit more compact than the pion. Last thing I want to tell you. So recently, well, it's already 20 years. So starting from the early 2000s, a new technique was developed to measure the electric and magnetic form factor at the Thomas Jefferson Lab in Virginia, United States, through the so-called Recoil polarization method. So what is this about? In this case, they were using a polarized electron beam, so where the spin of the electron is aligned or anti-aligned with the momentum, okay, of the beam particle. And once you now calculate the cross-section for a polarized elastic scattering, it turns out that the proton, which is not polarized in the initial state, becomes polarized in the final state. So there is essentially a spin transfer from the beam to the target. Okay, and the proton acquires actually two components of polarization. One is longitudinal, so collinear with the direction of motion, and the other is transverse. So it acquires both components. And through this technique, one can measure the ratio between the electric and magnetic form factor by measuring the ratio of these transverse with respect to longitudinal polarization of the final state proton. Okay. Then what you need is the energy of the incoming electron that you know, because it exists your beam, your outgoing electron that you know because you've measured, okay, and the mass of the proton and the scattering angle. Now, by doing so, a big surprise arrived. So in this plot, you see here the ratio between electric and magnetic form factor for the proton, okay, normalized by the anomalous magnetic moment. And this data here, the open points, are what you obtain by the Rosenwood separation technique that I showed before. Okay, and in fact, the two scale just by the anomalous magnetic moment. So the ratio is exactly around 1 when you correct for your magnetic moment. Okay. However, with this new polarization technique, the data have a completely different behavior. You see, the ratio is not constant over q squared, but goes down actually quite rapidly down to 0.1, 0.2 at the end. Okay, so this was of course a big problem, how to understand this difference, because the physics underlying is the same, but the technique is different. So rather than being constant, the ratio decreases with q squared down to 0.1 at 8 GeV, as you can see here. Okay, and this corresponds to say that the electric charge distribution extends to a larger radii than the magnetic one. So the magnetic moment is more compact than charge distribution in the proton, according to these results. Now, the solution to this puzzle is not completely solved yet. There is still a lot of debate, but the main explanation is that one should, if you don't limit yourself to one single photon exchange, but to a double photon exchange contribution, this is an higher order QAD fact that can contribute to your cross-section, then it turns out that the Rosenblood formula does not take into account this, okay? Or if you want to take this into account, the formula will change quite significantly, so your results are not actually correct, whereas this does not make any difference for the polarization technique, okay? So the favorite explanation for discrepancy between the two methods is the contribution of these two gamma exchange, which might result in a large correction for the Rosenwood separation and hardly affecting the double polarization condition. Okay, that's it for today. We continue tomorrow with now the inelastic and deep inelastic scattering regime. Any questions from home?
Well, or maybe for tomorrow if there's no time. I was just wondering, in those experiments, practically, so you aim a beam of electrons to your target, and then you've got to measure very precisely the form momentum of the outgoing particle to measure the Q2, right?
Yes.
So you don't work at constant Q2. You're going to work at the beam energy, and then you get whatever you collect.
Yeah, you have to vary the beam energy. This corresponds to varying q squared, the way I shown before.
Okay.
So you get a different point at different q square values, and so you have your q square distribution at the end.
Okay.
Okay. So see you tomorrow.
See you tomorrow.
Sorry for being too long today.